All right. So from the last model, your driver is going to have to change. I went over this with you guys, but I want to get in the recording. Your PID, the actual base of it, won't have to change at all, but the output no longer is going to be a tractive force. It'll be an accelerator pedal position. And what you'll do for your accelerator pedal, you want to saturate that output from 0 to 1. And for your brake, you want to saturate it from 0 to -1. What we're assuming is that the driver is never going to be pressing the brake and the accelerator at the same time, which really they shouldn't. So, for the brake system, this one is pretty simple. So you take in the brake pedal position, you multiply it by a brake gain. That is, in our case, the maximum braking force available. And then from there, you'll split it into conventional brakes up at the top here and regen brakes at the bottom. For your friction brakes, it's going to be 1 minus your brake fraction. So if your brake fraction is 10%, then really it's your regen brake fraction. So 10% of your brake is going to come from your regen, and 90% is going to come from your friction brakes. So it'll be 1 minus your brake fraction, and that'll just be your friction brake force. That'll come back in the DriveLine model. For your regen brake, you want to take multiply it by your brake fraction, your total force, and then you want to multiply by the wheel ratio. So now you have the torque at the wheels, and then divide by the gear ratio of the final drive. That'll give you the torque at the motor that you need. And then you should use a switch like this one and have velocity as the input. The reason for this is that in regen braking, you actually want to not do any regen below about 5 miles an hour. Motors are not super efficient at low speeds and low torques. So if you're coming to a stop, you don't want to have your regen on. So since this will be in meters per second, I would set it at about 2. I think it's actually like 2.2 something, but around 5 miles an hour is fine. And so what the switch will do is if it's greater than 2 miles an hour, it will use this one. If it's less than 2 miles an hour, it'll use the bottom input. And for that, you just want to zero it out. And then I have this saturation here just to keep sanity, but it's not necessarily needed. I limit it from 0 to -500 just to make sure that I'm not going to exceed the total brake force capability. So for the motor, you've got 3 inputs: your accelerator pedal position, your motor speed in radians per second. That's calculated in the DriveLine. I'll go over that when we go to the DriveLine model. And then your regen torque. Oh, this is the one that doesn't have it. Dang it. All this would be here. I'll actually just start making it. So dynamic saturation. What you want to do is you want to take your regen demand and have that be what's going to be saturated. Your regen limit, which I'll go over how to calculate that, you want that to be the lower bound because it's going to be a negative number. And then your upper bound is just going to be a constant at 0. Bam. Right. Now for the actual torque limit, you're going to take in your APP and your motor speed. So what you want to do is take your motor speed in radians per second, divide your maximum motor power. I think for this one it's 200 kilowatts. It might be 100 though. Divide by your motor speed. That'll be your power limited torque, and then your actual maximum torque. Take the minimum of that. This is really similar to what you guys did in the PID for the driver model, and that's going to be the maximum torque that you have available. If you multiply that by your accelerator pedal position, then you have your propel torque. That way, 100% accelerator pedal is as much torque as you can possibly provide right then, and then 50% is half, etc., etc. And then take that same limit, multiply by negative 0.5. In regen, we generally don't go to full power or full torque on the motor. So negative 0.5 will put you around what you would realistically see in a regen braking system. And that regen torque limit is what gets fed it back into this subsystem. So then from your regen torque, which is going to be a negative, your mechanical torque here coming out of the motor torque limit system, that's going to be positive. So for me, I just add them together. Again, it's a sign thing. If your regen torque is going to end up being positive, you want to make sure this says negative. But as my regen torque is negative and my mechanical torque is positive, I can just add them together. So that's going to give you your torque out, which is one of our inputs. The other output that's important for the battery model is the required motor power input. So you take your motor torque and your motor speed, and you do the loss calculation. This is a little bit messy as I have it displayed right now, but this is exactly the equation given to you on the assignment sheet. It's just implemented in Simulink. The KC, KI, KW, and or I guess K omega and C values, those I also put on the assignment sheet. Those should be actually pretty close to HEVT's motor, the one that's in the car right now. We haven't dyno tested that motor, so maybe it's not exact, but should be pretty dang close. And from that, you can get the power loss at the motor. Something else that I also do in this block is I log the mechanical energy in the motor. If you take, you take motor torque, motor speed, multiply them together, you get the motor power, and then I just integrate that to get the mechanical energy. So from that P loss, you can see here I do the same thing I did before. I break it out into propel and brake losses, and I also just have my overall motor losses by itself. And then to get the total motor power needed to produce what I'm doing at the output, the mechanical output, I multiply motor speed, motor torque, get the motor power out, add that to my losses, and I get the motor power in. The motor power in, break it down into the electric power needed for the motor, as well as the electric power during propel, the electric power during brake. Something to note here is that your P out will actually always be positive, or not P out, sorry, your P loss will always be positive. So if you have your P out, so you're driving the vehicle, you're putting out a positive torque, so your P out is going to be positive, your P loss is going to be positive. So the power needed to overcome those losses is greater than the power that you're actually outputting. And then if you've got a negative P out, so you're doing regen braking, you have this large negative number, but you add your losses to it. What that means is the power that you're actually getting at the battery pack is less than the power the mechanical power that's going on at the input to the motor. So the way that we have this set up, it doesn't matter if you're in regen or if you're in propel, your losses are going to work against the motor output. So that's how you get the motor power in. For the DriveLine, this is where we get the motor speed, what we calculated in here. We take the glider velocity in, the motor torque, as well as the friction brake force that we had earlier. Here what we're doing is we take the motor torque in. This is a sine block, so if we have positive torque, the output of this is 1. If we have negative torque, the output of this block is -1. Multiply that by the spin loss, and then if the So if the motor torque is less than the 6 Newton meters that we're losing to the spin loss, it's not going to be able to actually spin the wheels. So the purpose for this switch here is that when we're below 6 Newton meters, it basically rises up to match the torque being produced. But then after that, it switches over, and the torque loss in the drivetrain is actually going to be just 6 Newton meters. So it's not going to keep building after that. That's the purpose of that switch. And then here, because my output here is actually the same sign as the motor torque, I need to subtract it to get the actual output torque, since it's torque minus torque loss. Multiply that by the gear ratio, divide by wheel radius to get the I just covered that up, to get the force at the wheels from the motor, and then take the friction brake force, which for me is already negative, and add it together to get the total force output that you can input to your glider. To get the driveline losses, take your spin loss. You want to do it after the switch so that you get the actual spin loss that's going on. Multiply that by motor speed, which you can calculate from taking vehicle speed and multiplying by the gear ratio and dividing by the wheel radius. The reason for this is that here we're going from wheels to motor, not motors to wheel. It might get a little confusing because in one we're not going the same direction for torque and speed. For torque we're going motor to wheels, speed we're going wheels to motor. So the actual gain here is going to look the same as going from motor torque to wheel force. But multiply by G, divide by the wheel radius, G being the gear ratio, to get the motor speed. So this is not needed if you might need it if something is going weird in your model. I have it here because of a different bug that I was having. It's not needed in all cases, but if you're having a weird issue where motor speed is going negative, this is something you can do to try and figure out, is that what's causing my issue? If I put a saturation block on my motor speed from 0 to infinity, so I'm only letting everything else see positive motor speed, if that fixes the bug, then probably that would be the only way to fix it. If it doesn't fix it, it means that's obviously not the problem going on. So take motor speed, take your spin loss, multiply them together to get your driveline power loss, and like everything else, we break it out into propel, brake, and total losses. And then you can output your tractive force. Your glider is unchanged from previous gliders, so you shouldn't have to do anything to that to get it to work. If you're having bugs with your glider model, shoot me an email with specifically what it's doing. Most of the bugs that you might be running into probably won't be too difficult to solve. I hope I can solve them just over email, but if not, we've still got tomorrow and Friday to go over them, and then after break we can also sort it out. But you don't have to if your glider is having problems, don't have that keep you from working on the other models. Take just your motor model. Take just your motor model and make sure that works as expected. Take just your driveline model and make sure it works as expected. That way, if you know which individual subsystems are perfectly fine, you don't have to touch them. You can concentrate on just whatever is going wrong. You don't have to worry, is this a problem in my driveline model or is it a problem in my motor model? If you test each one individually, you can identify exactly where it's coming from. So, yeah, that's going to be it for this recording of motor, driveline, and brake system.